Good afternoon, everybody. My name is David Johnston, and it's going to be myself and my colleague Dominic Miles Shenton, both from Centre Built Environment, Leeds Metropolitan University, that are going to give you a brief introduction of our experiences of co-heating testing in the UK. Myself, I'm going to talk briefly about new dwellings and the co-heating testing that we've been involved with new builds in the UK, and Dominic is going to follow me later on discussing existing properties and the ways in which we've used co-heating testing to look at interventions as well. Just give an overview in terms of Leeds Met's experience of co-heating testing. We've undertaken in excess of 50 co-heating tests since our inception as a group in the UK. The very first one was undertaken almost 25 years ago in the 1990s as part of the York Energy Demonstration project, but the majority of the tests that we've undertaken, the majority of the 50 or so, have been undertaken within the last decade or so. We've undertaken tests on a very wide range of dwellings. We've only undertaken them on dwellings. Most of our work concentrates on new builds. The majority of the tests have been on new build, although that's increasingly changing, and we're undertaking more tests now on existing dwellings as well. We're undertaking a range of dwelling forms, ranging from some of the most complex ones to undertake co-heating tests on, which are apartments, through to detached dwellings, terraces, various different bungalows, so different dwelling forms, semi-detached, detached, and very different construction techniques, ranging from masonry cavity, which is a traditional form of construction in the UK for new build, solid wall construction, solid brick wall construction in terms of existing properties, through to more modern methods of construction. We've tested hempcrete dwelling, for instance, and we've also tested dwellings constructed using structurally insulated panel systems as well. We've used the test not only to work out the heat loss coefficient of new and existing dwellings, but also to measure the impact of various fabric improvement interventions. So, for instance, we've tested dwellings prior to any fabric interventions, and then tested the dwellings again once we've had particular interventions to begin to understand the impact of these interventions on the performance of the building fabric. We've also been fortunate enough to undertake tests under controlled conditions as well, and I'll talk a little bit about that briefly later on. And we've also undertaken repeat tests on a number of dwellings as well. So one of the few institutions that's been able to do that. So quite a broad range of tests that we've actually undertaken. One of the things that's quite important to know is that not all the tests have been successful. We've had some difficulties with some tests. It's not always possible to undertake a successful co-heating test, no matter how hard you try. Because it's in the field measurement, you are at the hands of the weather, and in some cases we've not been able to achieve successful results undertaking tests. One example here is a block of apartments in Middlesbrough, which we undertook the tests in March 2012. During that period of time in the UK, normally the weather conditions are sufficient that you've got a high degree or a reasonable degree of achieving a successful test. But unfortunately, when we undertook the test on this particular apartment, there were very high levels of solar insulation, and because it was a very small apartment with a large amount of glazing, that had a big impact on the actual test itself. We extended the test period. One of the things about co-heating testing in the field is it's not really a fit and forget test. Certainly using the protocol which we've developed at Leeds Met, is that you can't really undertake a test and leave it. We did undertake a number of interventions with this particular test, but out of 76 days of testing, we only got 11 days worth of usable data, partly because there were problems. This particular apartment block had a communal biomass heating system, and it was very difficult to isolate the heating to the particular apartment itself. Despite the fact that we guarded the apartment, so we made sure that all the surrounding apartments were heated to the same mean elevated internal temperature as the actual test apartment, so 25 degrees centigrade, so that there was no heat transfer from adjacent apartments to the test apartment. What we did find was there was significant heat transfer through the structure of the actual apartment building itself, which was concrete frame. So they were unaccounted for heat losses occurring all over the place in apartments. And apartments are a very, very difficult dwelling form to actually test. So it's just important to realise that no matter how hard we try, sometimes these tests can't be, it's not possible to be successful all of the time. In terms of the co-heating tests that we've developed, we've been able to use our expertise that we've gained over the last 25 years or so to develop a co-heating testing protocol. The first iteration of that was published in 2010 by one of our ex-colleagues led that, Jez Wingfield, and that was adopted as part of the UK Government's Technology Strategy Board's Building Performance Evaluation Programme. We've since revised this and presented it to the IEA Annex 58 as part of building characterisation work, and it contains considerable amount of information on undertaking co-heating tests, ranging from the actual test procedure itself, the equipment required, where you may want to think about locating the equipment, the types of equipment required, and various ways in terms of issues to consider, depending upon the type of building you've got, thermal mass characteristics, and also data analysis techniques as well. And there's a web link on there in relation to the latest version of that co-heating testing protocol. In terms of recent results that we've got in relation to co-heating testing, we've been involved with the UK Government's Technology Strategy Board Building Performance Evaluation Programme, and we were fortunate enough to test 7 new build dwellings as part of that programme, a range of different dwelling forms and a range of different types of construction. And the graph in front of you shows the results obtained from these particular tests. So you can see in blue the measured heat loss coefficient, in red the predicted heat loss coefficient, and then in green the actual difference between the two. And in all of the cases, we, as you would expect with dwellings in the field, the measured heat loss coefficient was greater than the predicted heat loss coefficient. I think I've got the colours wrong on that graph actually, greater than the predicted heat loss coefficient. One thing to note is that in terms of predicted heat loss coefficient at Leeds Metropolitan University, it's important that what we do when we compare measured against predicted is we don't compare the design intent heat loss coefficient against that which is actually measured. Because quite often what's the case is that the design varies quite considerably. So in terms of our predicted heat loss coefficient, the predicted heat loss coefficient is our best informed guess, taking into consideration what we've observed when the dwelling's actually built, of what the heat loss coefficient actually is. If we actually look at put the dwellings into our database of 26 new build dwellings, you can see that there's quite a range of performance in terms of actually measured, the correct way around on this particular graph, measured performance against the predicted performance. And you can see in terms of the yellow ovals, that's the 7 dwellings which were included as part of the Technology Strategy Board's Building Performance Evaluation Programme. Now, the sample, unfortunately, is not a random sample, because these dwellings are dwellings that have been presented to us as part of various different research projects, but this is the most comprehensive database available in terms of dwellings that have been measured in terms of undertaking co-heating tests. If we actually look at the percentage difference between measured against predicted performance, predicted heat loss coefficient, this is a sort of graph that's quite often presented, but unfortunately very often misinterpreted. You can see that there's a very wide range, ranging from about 4% discrepancy and measures versus predicted performance up to 140%. But one of the things that this graph doesn't show you is it can unfairly penalise dwellings which have a very low heat loss coefficient, such as passive house dwellings. So passive house dwellings can be very well insulated and have very low heat loss coefficients, so small differences in heat loss coefficient can present themselves as quite a large percentage difference between measured and predicted performance. If we look at a more appropriate way of presenting the information is to look at whole building mean U values, and that's certainly a more appropriate way. If we look at whole building mean U values, that's something which contractors have a much better understanding of as an actual U value. The range, again, there's a very wide range in terms of U values, but you can see the columns in red are those dwellings that we tested as part of the Technology Strategy Board Building Performance Evaluation Programme, and they all perform towards the better end of the range of performance. In terms of coheating testing as well, there's been certainly some press in the UK recently regarding reliability and repeatability of the coheating test. And as I mentioned earlier, we've been fortunate enough to undertake coheating tests also within controlled conditions, and we did that at the Salford Energy House at the University of Salford. Now that's I think it's a 1920s semi-detached dwelling, solid masonry dwelling, which has been built within an environmental test chamber. For undertaking such tests, it is possible to remove a number of the conditions which can affect a coheating test and ultimately determine whether a test is going to be successful or not. For instance, weather conditions can be controlled and there's no solar insulation. In terms of the work that we've done within this controlled test environment, we've undertaken two separate tests at the Salford Energy House. One on what we term as a virgin dwelling, so that's the actual Salford Energy House as was constructed within the actual test chamber without any intervention measures undertaken on it. We undertook that test under a range of different mean internal temperature with a mean internal temperature of 25 degrees centigrade with different external temperature conditions which can be controlled by the environmental chamber, and the heat loss coefficient was very similar under each of the three conditions. We've also undertaken coheating tests on the dwelling at various different stages of refurbishment as part of another research project to measure the impact of various different fabric improvements within again controlled conditions, and the tests from both sets of these tests compare quite favourably the results to those undertaken using an alternative testing technique, the cube test, which there'll be a presentation on later on today. Also, in terms of reliability and repeatability of coheating tests, we've also undertaken some repeat tests on one particular dwelling almost 3 years apart, and they have shown in terms of repeatability of the test that there's virtually no difference in heat loss coefficient. And by undertaking an independent t-test on that, there is no significant difference between the heat loss coefficients as well. So that gives us a great deal of confidence in the actual test protocol and the test actually itself, that it can be repeatable. We have also, one of my colleagues has also been involved in developing alternative test methods. The existing test protocol can be quite labour intensive to undertake and involves a number of items of equipment which have to be installed within the dwelling itself. And one of my colleagues has developed what we're calling a simplified test method, where minimal equipment is required, just some temperature and humidity sensors, and instead of using electrical resistance heaters to input heat into the building, it's using the actual building's own heating system. Now, we've undertaken some, it's only at developmental stages at the moment, but we've undertaken some preliminary tests in the field on 2 separate dwellings of two different dwelling forms, one detached, one semi-detached, and they are of 2 different construction types, one masonry and one structurally insulated panel system, timber frame system. And the results that we've got from preliminary results and analysis of various results are encouraging. Further work on this is planned later on this month, where we intend to retest one of these dwellings, and we'll report on those results when they become available. But we're hoping that the simplified method will mean that that there's essentially going to be a more commercially viable test out there, which will hopefully be much less expensive, much less labour intensive, and be able to be undertaken within a shorter period of time as well. I'd just like now to pass over to my colleague Dominic Mouth-Shenton, who's going to go through some of the testing work which we've undertaken on existing properties.
Hello everyone. I don't know whether it's the economic climate at the moment, but there seems to be less and less people wanting to measure just standard new build dwellings in the UK. Most of the recent tests that David's been looking at have been of low energy dwellings. And most of the work now that's coming in seems to be looking, rather than just getting a general heat loss coefficient for the dwelling, to look at before and after work on renovations, just to see how successful they are and whether they're giving the energetic and financial paybacks that are expected from them. So this, what you can see on the screen now, is a house that we're currently testing at the moment, or just dismantling the test. And it's just a quick video walking through just to show you actually what we do on the co-heating test. This is a back-to-back terrace house. It's got separating walls on 3 sides. We tested it in February last year, and in its original state, and now we're just testing it again with internal wall insulation put on the front of the house, and the ground floor and roof insulated as upgrades. You can see the weather station on the front. Inside the house, because we've got 3 separating walls, we have to know how much heat is actually going into each of the neighbouring properties, and so heat flux sensors on the adjoining elements, as well as doing our heat flux sensors, as you can see there, on the external walls with the internal wall insulation fitted. There's one on the bay roof, and yeah, you can see that it's only a small house, and so it's actually quite difficult to put all the stuff in there without it actually interfering with sort of like the measurements that we're actually taking. But a quick one, heat flux sensor are recorded on data loggers. Those we tend to put this setup once on each floor. You can see everything is plugged into the wall. It goes through a kilowatt-hour meter, so we know exactly how much energy is being put in there. There's a temperature controller. It's RTD temperature control, so we've got a fairly good control on there. You can see the temperature set to 23 degrees. It was 22.8 in there. We tend to get very little variation from the actual temperature. The circulation fans keep the temperature stable throughout that actual room on that actual floor. We have the same setup on every single floor. Heat flux sensors strategically placed. We use a thermal camera to identify the areas where we're going to stick those heat flux sensors. We don't just sort of like put them down there at the moment. This house had a cellar. A big problem with the cellar was, you'll see when the light goes on. Again, with the heat loss going into the cellar, it's also the main infiltration zone. So as we found out there, if you heat the cellar up too high, because the infiltrating air is coming from the cellar into the whole house, what that will start to do is drastically raise the moisture levels within the house itself. So basically we put the same equipment in the cellar, so we've got an idea now of how much heat is being lost from these cellars, from these basements. But yeah, we couldn't just keep that at the same temperature as the house because of this moisture issue. So yeah, again, heat flux sensors on all the elements there, so we know where the heat's going from the cellar. Temperature sensors directly underneath where the heat flux sensors are in the kitchen above, so we know how the improvements in the ground floor are performing. So back up into the kitchen. Yeah. So again, we've got sort of like RTD controls temperature and circulation fans, keeping that. And the circulation fans also stop any stratification of temperature within the rooms itself. We've got these temperature sensors, or temperature, humidity, CO2 sensors situated all around the house. Again, another heat flux sensor on the separating wall to that side. This house had internal wall insulation fitted, so although we've only got sort of like a few heat flux sensors measuring the heat going through into the other walls, on the front wall where we've got this internal insulation fitted, we're looking at that in a bit more detail. So you can see there is a much denser array of heat flux sensors set there. So we've got an idea of what's happening with it close to partition wall junctions, close to reveals. We're also measuring the surface temperature and the temperature that probe goes through and it touches the wall, so we know the temperature at the insulation external wall interface. And again, on the other side, we've got the same co-heating test set up with the circulation fans, the same heat flux sensors there. And on the external wall, we're looking at it in a bit more detail. Again, the weather station that was put on the front of the house, we're also logging. The data loggers, we can actually phone up using a modem connection from our office. So we've got, if there is anything that needs to be acted on quickly, if something's gone down, if something's not performing properly, we can just go across there and sort of like see what's happening and sort it out as quickly as possible. Because as in a lot of these cases, we only have a very limited time window as to when we can actually perform these tests. Up onto the top floor, the final bedroom, again we've got these heat flux sensors on the separating walls. We've got an idea of how much heat loss is going through there, but you can see just how complicated some of these buildings can be. If you just look at the roof structure in here, we've got a dormer roof, we've got dormer cheeks, we've got sloping roof section, we've got a knee wall going to a cold roof void at the front of the house. We've got these drop soffits with a steel beam going through, and we've got another flat, or an area of flat roof, cold roof there, which has just got loft insulation at ceiling level. So it might sound easy just measuring something before and after and seeing what the difference is, but it's trying to tie up where these differences occur. So, so basically that's that video. So that's the house we're currently doing. There's a couple of other buildings that we've tested the interventions for. On the left-hand side, you can see a 1930s semi-detached house, which we measured at 3 times. It went under a 2-stage intervention or refurbishment. The first stage was just doing the standard things they do in the UK, what we'd call a decent homes upgrade. So cavity wall insulation. This house had extensions, so they're actually internal cavity walls as well. That used to be external walls. They were also filled with blown fibre insulation. It had loft insulation. The floor over the garage had to be repaired. That was insulated. And some measures were taken to reduce the air leakage as well. A suspended timber ground floor was boarded over and the chimney capped. And then, so we tested it again then. And then the second intervention, we were aiming at this aspirational government target of 80% reduction in CO2. And so to achieve that, 175 mil of EWI, external wall insulation, was fitted. The loft insulation was actually added to join up with that external wall insulation at the eaves. Northern Entec triple glazed windows. The floor was dug out and a solid floor with 200 mil of extruded polystyrene placed underneath, and additional air tightness measures were done there. So extra sort of like sealing on the service penetrations, and actually sealed around the built-in floor joists. So that was an existing one. The houses you can see on the right are actually new build, not low energy houses, just ones that were built to UK 2006 building regulation standard. And we tested some similar to this before and knew they performed particularly badly. So what we did on these ones was tested them in their original state, then we filled the party wall cavities with mineral fibre to reduce the heat loss from them. And then the second step you can see in the bottom picture there, these houses had 40 mil of PIR partial fill external wall insulation. We knew that that didn't perform anywhere near as well as the design figures were supposed to, so we actually topped that up using blown mineral fibre. Some certain problems in that, there were areas such as under cavity trays that we actually couldn't drill into from the outside, as puncturing these trays would present moisture ingress issues. So the results we got from those were very interesting. You can see the three sets of data on your left show us this 1930s existing building. When we tested it, it was actually about 25% lower than the predicted figure, and basically that's because our predicted figure was wrong. And what we found out subsequently on other ones is the standard way of calculating the predicted values is using government figures in the UK based on a protocol called RDSAP, which uses the age of the dwelling and what certain observations you can make to give you U values. We used those U values, we got a much larger predicted heat loss than we actually measured. After we'd done some of the renovations, we had a much better idea of how the house was constructed. You could see there that we effectively measured the same as was predicted. By the time we came to the sort of like the more capital intensive, if you want to call it, upgrade with the external wall insulation, we had a much better idea of what every element was, and we could get a much more accurate predicted figure. Of course, by then, the amount we measured sort of like ended up being sort of like substantially more than the predicted figure. The other two sets of sets of bars on there show these two new build houses where we sort of like topped up the party wall, and again, sort of like saying, they weren't low energy houses, but we went from being sort of like double what the predicted heat loss to filling the party wall. We got sort of like just slightly more, and then once we actually filled the external walls and topped up this partial fill insulation, we ended up with about 10% greater heat loss than predicted. So a substantial improvement and much more like these people expect. So I think that's about it then. We'll pass you back to Alex.